So welcome everybody to the next talk. Before I start, a little word of warning. When I submitted the talk, I thought there are 2 or 3 things about consistency that would be worth sharing, and I looked forward to and was quite confident to create a talk of 45 minutes roundabout. But then I started to prepare this talk, and while preparing it, I suddenly figured out when I talk about these 2 or 3 things, I have also to talk about these 5 other things, and if I talk about these 5 other things, about these 8 other things. And so to cut a long story short, I did it again. I crammed way too much stuff into the next 45 minutes. So sorry up front if I might inflict some kind of mental illness on you in the next 45 minutes. I try to keep it as little as possible. But at least you're warned. It's your last chance to flee, by the way. Anyway, so my name is Uwe Friedrichsen, working for a quite cool company called Codecentric. That's been the advertisement break, actually. That's enough of that. And I'm not going to spend a lot of time on my history also, because we've got other stuff to cover. And before we really become serious, some kudos first. A lot of this talk was inspired by some blog post from Adrian Collier. By the way, who knows the morning paper? Oh, way too little persons. It's a great blog post. So usually Adrian picks a research paper or a conference paper and walks through that and recaps that. It's a great read. I mean, it's a lot of stuff, but it's a great read. And once in a while, he does some original blog posts, so usually referencing about 20 papers in there, or 50 papers, or anything like that at once. I'm not sure what he's doing besides writing this blog post anyway. And one of those, this was a blog series actually, gave me the idea for this talk and some other, and then I went along, and you will find a lot of these references in here on the slides, which you can download later on. I will upload them to my SlideShare account. There are all the references in there, so if you want to dive deeper into it, you'll find all the stuff in there. Okay, let's become serious. Talking about consistency, and whenever we talk about a topic, it makes some sense to look where we're coming from. And what's been consistency in the past? Usually it was these 2 things, relational databases and as a transaction. There was also another storage medium called file system, but when we reasoned about consistency, we usually didn't think about file systems, usually about relational database, at least in the last, so let's say from the early 90s or the mid 80s till, say, 2010. That's predominant storage medium here. Looking into this relational database, it's this one database to rule them all. I mean, it's a great all-rounder. It's got a rich schema, and rich access patterns are possible. We have the SQL language where we can do a lot of many things. Some of them make a lot of sense, some of them don't make so much sense. Originally, we have to keep in mind, was designed for scarce resources, and many people are still thinking in this way. I mean, when relational databases came up, storage, CPU, backup were really expensive, and network was slow. So, and many people are still thinking this way, even though in a cloud environment, and today's world is different. And based on these scarce resources, usually we ended up with this big shared database, because replicating the data was expensive, network was slow, and licenses were expensive, operating a database was expensive, everything was expensive. And so we used that, and we figured out it was an easy integration model, which then led us to data spaghetti usually. So this huge monolithic data model, which gave us a lot of problems. And which is usually one of the biggest challenges whenever we try to split the monolith. Usually splitting the database. So much about relational databases. And now the consistency model. Most of the databases, relational databases, came with this as a transactions. I mean, we know what it is. Meanwhile, and some people come around, and most people are really used to that still, saying everything needs to be an asset. we need asset transaction. I usually ask them why. And they then say, yeah, it's a business requirement. I say, it can't be a business requirement because the real world doesn't know asset. There is no asset out there in the real world. The real world, in best case, is eventually consistent. Usually it's inconsistent. So there can't be a business requirement for an asset transaction. Still, it's very valuable to think about asset transaction because it's a great programming model. Because we don't see any anomalies, and so it's very easy to reason about that. It's very easy to handle from a developer's point of view. I mean, I start a transaction, I do something, nothing else seen outside, I commit it, either everything works or nothing works, and I'm done. No anomalies and nothing else, so great. Nothing I have to care about. But, that's the big but. Reality is different. Sorry to talk about that, mentioned that. Because whenever most people think about asset transactions, they think about serializability. Whoa, this won't work. Anyway, about serializable transactions. And quite often, databases don't run on a serializable isolation level. They run on a lower consistency level. So you see anomalies in your transactions, and most people don't know about it. It's usually that case when you've got this production failure, when your data became inconsistent and you try to reproduce it and you're not able to do that. So it must not happen. There's no way to happen. I perfectly programmed it right. Right, because your database did something different. Not what you expected. Digging a little bit deeper into that, if we look into the SQL definitions, it defines 4 isolation levels. And the isolation levels are basically defined in terms of anomalies that can happen. And standard ones are here. The first one is the dirty read. So you start in a transaction, you modify a value, and another transaction sees that value before you committed the value. That's a dirty read. The fuzzy read or non-repeatable read is that for the next 2 ones, there are a lot of different possible interpretations. Also, the ANSI standard is not very specific about that. The weak interpretation of a fuzzy read is transaction 1 reads the value, transaction 2 changes and commits the value, transaction 1 rereads the value and sees the new value. So that's the anomaly then, so that you see then after the commit, you see the other value. The hard interpretation is that it must not, that it is possible at all that if you read a value in one transaction that you can modify that in another transaction as long as the first transaction is not aborted or committed. That's the hard interpretation. And phantom read is basically the same thing, but on a predicate level. So, which means that you have a where condition or an aggregate function in there. So I select the sum of the values from a table where following condition is met. The big difference between the non-repeatable read and the phantom read in here is that usually to prevent that one, you have a write log usually on several rows just. Here you usually need a write log on the whole table. And in ANSI SQL definition, a phantom read is only protecting against inserts, not against updates and deletes, by the way. So there's quite a bunch of interpretations possible. And if you look at Berenson and the other guys who wrote the paper, they extended that model by the lost update ID anomaly. Lost update is basically that you have 2 concurrent writes to a value and the first one is lost. And then the lost cursor update, which is extended to cursor semantics, which is quite important because this one is prevented. So this cursor stability isolation mode is protecting in that one. And there are 2 ones which they also introduced, which happen quite often, which are bound to constraints between values. So read skew means you read a value x in transaction 1, and then you modify value x and y in transaction 2 and commit that one, and then you read y in transaction 1. And if there's a constraint in between, it can happen in the first transaction that you see an inconsistent pairing of the 2 values because the change modified y in a way that it doesn't match to the old x anymore. And so it's a generalization of the non-repeatable read. And the right skew actually is something which happens quite often in systems where you've got snapshot isolation, or which can happen to you. Multi-version concurrent consistency. Here you read x and y in transaction 1 and in transaction 2. Transaction 1 changes x in a way that the constraint is not violated. Transaction y changes y in a way that the constraint is not violated. But both together end up in an inconsistent state. All kinds of anomalies which can happen. And if we have all these anomalies over here and we have the different kind of isolation levels, we're not going through all of them. But if you look into them, you will see that interesting are all these cells here where it's possible in or sometimes possible, because this means whenever your database runs in such an isolation level, this anomaly can happen. And except for serializable, everywhere anomalies can happen. And now, let's look into the default and maximum isolation levels some SQL and new SQL databases are running in. So look for the default level. S means serializable as a default level. 3 databases out of 20 or something like that run in serializable as default. And maximum, there are a lot of databases who don't even offer serializable as a maximum isolation level. So whenever you think and reason about your programs, your database is very likely to do something different. Sorry about that. So let's wrap up the past. Relational model is a good trade-off. ACID makes our life easy as developers, but unfortunately, it's not everything is ACID where we think it is. Let's leave that for a while and go to the present after destroying the past. Today's world basically is, who did this animation anyway? Oh, it was me. Shouldn't have done that. It's basically defined by cloud, microservice, NoSQL, and base. And yeah, I know many companies are not yet there, but let's assume we are all there. Looking briefly into cloud, I mean, this combination of self-service, elasticity, and pay-per-use, which gives us a great resource provisioning model. And if we do it right, it improves our autonomy, so in terms of development and also in operating systems, response time in terms of cycle times, not latency, cycle times, elasticity, and it can even be very cost efficient if we do it right and have the right business case. On the other side, trade-offs is we go out into distributed hell because we usually scale out, and we have a reduced availability of the individual resources, which makes us handle that or requires us to handle that on the application level. And it also gives many databases a hard time because they can't deal with that. They always expect that the infrastructure is always there and is always working. So, which gave rise to many of the NoSQL solutions, by the way. Microservice, on the other hand, basically, sorry for the simple explanation here, is the mapping of the organizational autonomy to the software architecture. That's how I usually describe that, or the enablement of organizational autonomy. So yeah, these properties, we've heard them all a million times meanwhile, so I don't need to repeat that. It also improves our autonomy, the response time, again, in terms of cycle times, so getting faster. We also heard that several times these days. And elasticity here. Trade-offs is they're a lot harder to design than a monolith. Let's put it another way around. We figure it out we figured out a lot faster if we did it wrong. because our application becomes brittle and slow and everything like that. Harder to operate, distributed by default, and so back to distributed hell. Which is interesting in terms of consistency is this shared nothing thing, so that we usually must not share any data between services and that we should try to avoid cross-service coordination. I'll come back to that later when we go to the recommendations. NoSQL, the third one in game here, is extension of the storage solution space. I mean, before, as I said before, we had relational database and file system, which is great, basically. But there are some gaps left over, and the NoSQL solutions basically try to fill those gaps. So they give us new options in terms of scalability, in terms of relaxed schema, definition, and evolution, and so this availability in the cloud environment we heard before. Trade-offs is the CAP theorem. I'm not going to repeat that one. We also heard about that a million times meanwhile, probably. And I come back to that a little bit when I talk about base transactions. And here, just a word of warning, so it's a little bit of detour here, a very short one. What I see quite often in this area is that the capabilities and limitations of the different solutions are very poorly understood. What I see quite often is when Hadoop came up, everything was MapReduce immediately, and then after a while, everything became MongoDB. And what I see at the moment is sometimes everything is Cassandra or whatever else. And so this one-size-fits-all mentality, and that's very, very dangerous. So just let's spend 2 minutes to describe why it's dangerous. If you think about a storage solution, you should think about the properties that you really need. And I identified about 8 dimensions what you should think about. So starts with scalability in terms of data and transactions that you need. You could also differentiate these by read and write transactions, of course. Latency, especially with respect to scalability. Your read-write ratio is a master-slave database with replicas for read and the master for writing. Is that okay for you or not? So, and then very important, so the schema richness and the access richness. So variability of the access patterns. That's where usually most of the solutions die. So that's what the where conditions in SQL is. That's access richness. Whatever can you put in behind the where. Consistency, of course, and then fault tolerance, especially if we think about cloud environments. And if you make a nice picture from that, and then, for instance, take a relational database and put that in here, what you see then is that relational databases have their sweet spot in access richness. I mean, you could basically put everything into the where condition, everything which makes sense and which does not make sense. And it works. Sometimes it's slow, but usually it works. And consistency, they are great in consistency. Besides that, sometimes they're not really running in this serializable model that we think of. On the other hand, if we take a file system, it's great in read-write ratio. It doesn't care. And you can store in there whatever you want. It scales a little bit better up there. So it's really fast. But we better don't talk about consistency for those. And access richness really kills us in combination with schema richness. Because if we want to have random access to the data, we have to be usually fixed record lengths. And so the access richness, the schema richness is then a little bit compromised. So overlaying these, we see there is some room for improvement up here. So fault tolerance, data scalability, transaction scalability. It's not one size fits all again. And let's take, for instance, here, NoSQL solution which tries to fill the gaps. Cassandra. It's a tool de jour at the moment. Cassandra does everything. And if we build our picture here, what we see, it's cool in terms of fault tolerance, data scalability, and transaction scalability. It's a great solution for that. And we have great support for read-write ratio and schema richness. The problem is, if we try to access the schema data, we get a hard time, basically, because everything besides accessing via primary key doesn't really scale. And consistency is la, basically. So key point here, or the key learning in here, is there is no one-size-fits-all for this. If you overlay that, all of these solutions have their sweet spot, and all the other solutions can take another storage solution. It's not limited to these three ones. You will find some sweet spots, and you will find some weak spots. So you usually have to combine those. So be very wary about this one-size-fits-all approach that you see quite often at the moment. Consistency, base transactions. It's basically a response to the CAP theorem. I mean, if we go distributed, so partition tolerance is not an option, and so we have to balance basically consistency and availability. So we can't have all three of them perfectly. So we have to balance these two ones because partition tolerance is an option. Yeah. Okay. Base transactions improve our scalability and availability. On the other hand, and trade-offs, temporal inconsistency becomes visible. So anomalies you will see, and you will have to take care about them on the application level, you as a developer. And that is an extremely hard programming model for most people. I've seen a lot of developers in the last years who think that they understood NoSQL databases, and they didn't, actually. It's a hard programming model. There are so many things that you have to think about and reason about, that you never had to reason about before when you worked with these serializable transactions. It's a huge difference. Some key readings. Brewer introduced the CAP theorem on base transactions in 2000. Pat Helland, one of his seminal papers. This one, in 2007, he wrote the paper, Life Beyond Distributed Transactions, and what he described there basically set the basics for base transactions for many years. So at least from 2007 till 2013, 14, so what base basically means, what the upper bounds of base is. And Shapiro and the other guys then introduced CRDTs in 2011, which gives us stronger convergent guarantees in eventual consistent systems. So if you start in this area, start with these three papers basically, and try and then move on from there. But we have this up in the top here. I mean, what you also see quite often at the moment is people who run around and say, you know, oh, this network is so reliable. Do we really have to care about this partition tolerance? I mean, this hardware is so stable, and that software, it won't fail, or it fails so rarely that we don't really need to take care about that, and we can maximize availability and consistency. So so partition tolerance, so we just basically cross that out and then go for maximum consistency and availability. Is that a great idea? No, it's not, of course. Before I show you some figures about network failures and latencies, let's recap the failure types that we have to deal with in partition tolerance. So it's not only about crash failures, that something works and then doesn't work. It's also about omission failure, that your connection becomes flaky. Sometimes it replies and sometimes it doesn't. And the arch enemy of distributed systems is in there in the third one, timing failure, latency. I mean, that's the real problem in distributed systems. It's not crash failures, to be honest. And response failures, getting the wrong reply, oh, sorry. And let's forget about Byzantine failures at the moment, because they're really nasty kind. And if you take those and look into the first two ones, then I have here from another paper observation from a study from Microsoft. And it's not because Microsoft is bad. They're running their data centers extremely well. And here, last sentence. The study found a mean of 40.8 network link failures per day on the 95th percentile, a lot more, with a median time to repair of around 5 minutes. And up to a week. So network failures don't happen rarely. They happen very, very often. And here's a study of latencies between data centers of Amazon. And Amazons are doing a terrific job in having low latency between their data centers. And still, you have numbers here, if you go multi-region, which are up to almost half a second. And this usually really kills your application very fast. Or actually very slow. And that's only the network, what I've been talking about here. I mean, we haven't talked about failing nodes, about faulty processes on the operating system level, which can enroll problems in your application, and everything else, which also materializes partitioning in distributed systems. So what can we learn from that? So you can basically read the next 3 slides on your own. Yeah, happens. And no, it's not an option. So, yeah, what you have to do is, sorry about that, balance availability and consistency if you want to scale out. So wrap up, present time. We go distributed, cloud, microservices, NoSQL database, everything else. NoSQL fills the empty spots. It's not a one-size-fits-all, it's alternatives, it's options. And base transactions give us a really hard time as developers. Okay, and let's have a brief look into the future. What can we expect in the future? I mean, the core question in terms of consistency is, can I only choose between this full asset and this full base? So everything's nice, easy to reason about, but not very scalable. Or everything's scalable and highly available, but a terrible programming model. There's a lot of research about that going on at the moment. We don't have anything really industrial strength about here, but I will show you where it's going towards. And most of the research starts here. I have to say, asset doesn't necessarily mean that the transaction needs to be serializable. And here's a big graph that Peter Baylis and his folks created in some paper where they said, down here is base, and up there is that asset, at least the 2 ways that we usually reason about that. And that's all in between. There's all different isolation levels. The red ones aren't highly available. They need some kind of coordination, of strong coordination between the nodes which are involved. But very interesting are the black ones in here. So, for instance, item cut isolation down here. That's basically the weak interpretation of a non-repeatable read. It just says the guarantee that you want to have here in this isolation is I read a value and I reread it later in the same transaction, I read the same value, always. We can achieve that in a highly available fashion, this kind of isolation guarantee. Predicate cut isolation is the same thing for this weak phantom read. We can even achieve that in a highly available fashion if we read a whole predicate condition and not only a single value or few values. Or monotonic atomic views, which extends the read committed, basically, which says if I see one value from another transaction, I will see all the other values, and I will never see from the other values any older value, which is also quite a nice guarantee. We can get that in a highly available fashion. And here, these they have one limitation. The sticky available transaction model is also a highly available one with one limitation. You always have to ask the same node. You can't just ask arbitrary nodes of your replica set or of your storage solution. So you always have to ask the same node. And the best thing you can get here is causal consistency, which usually is, say, in 95% of the time, it's all you need. Causal consistency says if one change of a value depends in a causal fashion on the change of another value, we always see them in this order. If 2 changes are independent, we don't know anything about the order. But usually we also don't care about that. I mean, we only care about causal dependent changes, usually. And if we all get them in the right order, hey, that's great. Again, the other ones up here, you don't get them this way, but the point is, we can achieve all that also in highly scalable systems. And we are not stuck with acid or base. There's a lot of options in between that we can, which is great. I mean, we don't need to choose only between easy reasoning model and easy programming model and no scalability at all, or great scalability and availability, but terrible programming model. We have everything in between, what we need. And now, sorry, I'm a German, there's a but. We Germans love to say but, yes, but. Here's another yes, but. And the yes, but basically comes again from Pat Helland, who has the tendency to write several seminal papers in 1 decade. The other one was building on quicksand in 2009, which he did. There's a lot of stuff in here, but the key point is again the last sentence. It also means that we must move the correctness and reordering semantics, so reasoning about consistency basically means that, up from being based on the system properties, so read and write through a database, to the application-based business operations, which means it's like with resilience. As you can no longer rely on your infrastructure to guarantee the availability of your application. You have to move that up in a distributed system on the application level. On the application level, you have to build your circuit breakers and all that stuff to make sure that your application remains available. It's not handled by the infrastructure anymore. And what he says is, if you want to achieve these properties in distributed, highly available systems, you also have to put the reasoning and path of the implementation of your consistency model away from just, hey, database, handle that for me, to I'm aware of what I want to achieve and put that on the application level. And so database and application development work hand in hand, and together they achieve the consistency guarantee that you need. So to translate that, yeah, it's no longer sufficient to understand and reason about distributed applications consisting of the data on the level of data store access. I mean, you can do that. The problem is then that the database has to assume the maximum generalized approach, and on the maximum generalized level, you can either go with serializability. Hey, it worked. Strange. Shouldn't think about that. And then you can even speak it. Or with full eventual consistency, so at the lowest level, because they can't make any assumptions on what you really need on the application level. And this also means you need to understand and reason about distributed application consistency on the level of application operation. And that is the hard part. That's what I almost never seen in real projects. I mean, real projects, what the people say, what consistency needs do we have? Can we get along with eventual consistency? Yes, okay, let's take base transactions. We can't get along with them, we need higher guarantees, oh, we need serializability. And that's it, basically. So they never reasoned about, differentiated, what do I need, or do I need here, in this place, high guarantees, in this place, low guarantees? They just take this everything or nothing approach. So yeah, I think that repeats it basically. Yeah, you have to analyze the consistency requirements, and applications, so our implementation usually also needs to contribute explicitly to the implementation of the consistency model. That's the problem with that, with all these nice things that we can achieve. And there's a lot of research going on in there, and a lot of papers around that are really worth reading. And so just to give you a little bit of an impression what's going on out there at the moment. For instance, here, Baylis and his folks, I mean, Peter Baylis is brilliant anyway, so a lot of stuff. This paper goes about implementing highly available causal consistency in distributed systems. So exactly this one here, causal consistency, and they even implemented a solution for that, but on a research level, not on an industrial strength level yet. So it's still way to go to have that in an industrial strength version. And or for instance, the other one here also, Bailey, they defined a new isolation level, atomic read, which is quite nice. So it's a changes of one transactions become visible in an atomic way. So they don't talk about it that they're written in an atomic way, but they become visible in an atomic way. And what you can build with that, for instance, is you can really build secondary indices with that, which scale. Because right now, at the moment, what you usually have in the databases is that if you want to have secondary indices on a distributed database, it just keeps the index information on the node where the data is. Problem is it doesn't really scale, because if you want to do an index access, you have to go out to all the nodes and receive the results from all the nodes. If you could sort the nodes in a better way, so the secondary indices that you can directly access the location, you would be a lot more scalable accessing on their highly scalable fashion, and that's what this paper describes. Or here, building consistent transaction with inconsistent replication. So providing a very fast way to really get asset-like transaction with asset-like properties on the base of an eventually consistent on the top on an eventually consistent system. And the low latency they implement by getting rid of a coordination protocol, which is usually used below any kind of transaction implementation on a distributed system. Still, it needs quorum, so it's not really highly available. And this one's very interesting because it picks up the idea explicitly that you have to involve the application. What it does, what they implemented is some kind of prototype where they use annotations to describe your consistency requirements really in your application, in all your transactions, so in your business activities, and then an underlying layer tries to enforce them. And the last one is quite interesting also. They go a different way and say, we provide you with very scalable exactly one semantics, and then you can build linearizability on top of that, and which is a great basis for providing serializable transactions again. And we have some others, just to show you two more. Basically, it's here's a very different approach. Many of you probably know that, the spanner approach, so the spanner and the F1 database from Google. So Google used a different approach, say, oh, we have a hard problem. We have to solve this time in a distributed system problem. Let's just throw hardware on it. So let's buy a bunch of atomic clocks and GPS receivers, and we solve it this way. I mean, it sounds a little bit funny, but on the other hand, what they showed us is there are different ways to deal with consistency problems. And some other ones, like here, which try just to speed up asset transactions in a way that they sort say, but also with application awareness, so we say, can we group our data in several partitions, in several parts, which are independent of each other, so that if we have a transaction over here and a transaction over there, that we can execute them in parallel and don't need to have any locking between them. But basically, that's again, application awareness, but a different approach. And a lot more, that's just a few examples. So what you see is, at the moment, there's a lot of research going on and a lot of presentations on the conferences and so on, where they try to explore these frontiers of consistency in distributed systems. And what I also see, before I wrap that part up, is that there's a lot more to come, basically. So there are some developments which I think will give us very different, provide with very different solutions somewhere in the future. So on the memory and storage level, there are some trends going on which will change the way we implement applications quite dramatically, I think. First of all, we have this idea of terabyte memory computers, which gives us the option, 2-4 terabytes of memory, RAM memory, which is usually enough for most operational databases of most companies have, just in memory. and so full in-memory computing of large data sets. So we don't need to scale out anymore or anything. We can in-memory, high speed, and so on. Storage class memory, very interesting. A lot of research going on there at the moment. So a lot of technologies which try to fill the gap between RAM and SSD. So as fast almost as RAM, but non-volatile, which is extremely interesting, which will give that. And things like remote direct memory access, so bypassing the CPU, accessing a remote memory of a different computer, and which is about 2 orders of magnitude faster than SSD access on your own system. So it's still slower than RAM on your own system, but it's a terribly lot faster than accessing your own disk. And so you end up with very different architectures. So this prerequisite of our whole system design that we had in the last, basically all the time since we are dealing with computers, that the most critical resource is the CPU. CPU is fast, cache is a lot slower, cache and RAM is a lot slower, and any persistent storage is terribly slow. That was the prerequisite to all our system design that we had, and how we build applications and how we build computers and everything. It's no longer true with these solutions, because keeping the CPU busy is no longer the core challenge. You need lots of CPUs to keep those systems busy. So it turns around, basically, which will lead eventually to very different system architectures and programming models. I don't know where it will end up, but there's a lot of things going on. And so what I also expect that we will end up with very different consistency options that we don't have any idea about that they exist at the moment. But maybe that's a talk in about 2 or 3 years, and we can talk about that, where trends going to. Okay, let's wrap up the future. That's strange, isn't it? Anyway, so we have a lot of options to balance the consistency constraints and the intricacy of the programming model in there. So it's not only acid or base, it's a lot of in-between. It's a very fine-grained room. But usually, there's a lot of but most of them will need us to also put some part of the effort on the application level to lift that up from the database level only to also the application level. The same movement that we've seen with resilience to create robust systems, basically. Okay, last part. If we put all of that together, what can we learn from that for our daily work? I just have a few recommendations in here, and they're definitely not complete, as always. I mean, it's only the few things I think about. So I didn't talk a lot about this cross-service communication in the rest of the talk, but all the ideas that apply to cross-storage communication also sort of apply to cross-service communication. So 2 recommendations from my side are: the first one is, don't try to coordinate right across service or storage boundaries. So this, can I have distributed transactions across several microservices? No, you shouldn't. You should try to avoid that with your last breath that you have. Usually it means that your design is wrong, that you have some kind of entity-based microservice design or something like that. And so if you go for domain-driven design to design your microservice boundaries, always remember that we're talking about domains, business capabilities, not about entities, if we talk about domain-driven design. Many people who mix that up, unfortunately. So it's not about a data model, it's about a business capability domain model. And we should try to keep the activation path of our application short as possible. So not crossing too many services or going for an event-based architecture. And the other one is that we should try to relax our consistency constraints between services and complement that with reconciliation approaches. Here are two very interesting concepts around which you could have a look into. The first one is the ideas of promise theory. So Burgess coined this one and he put a whole theory around that. So when we go back, go down from the level of guarantees, so deterministic, to promises, probabilistic. Yeah, we try to keep our promises as hard as we can, but we can fail sometimes. And you can really build on these concepts and you end up with different approaches to write communication between services. And again, Pat Helland, in his Building on Quicksand paper, his concept of memory guesses and apologies, which is a great concept in distributed systems. So we just have some memory at the moment. We don't know if it's perfect, if it's really the real state of the whole world. We just see our part at the moment, and we guess, and we do our best guesses. And if we are wrong, we figure out later, we apologize for that. That's basically the idea of that. And in distributed systems, you have to think about these approaches. And if we are on one service and we reason about how we design that, so our one database for our one microservice, first one is, really think about what's the right storage solution. No one size fits all. And then, what are your consistency requirements, really? I mean, that's the hard part of the work, really to figure out what guarantees you need and which you don't need. Then, again, if you decide for ACID transactions, be wary of serializability, because usually your database, your SQL database that is running in your company won't run on serializability, so serializable isolation. It will usually run on a lower level because, as I said before, serializability usually means that you have a full table log as soon as you have a where condition in your if you have a predicate in your in access pattern, and you don't want to have a full table log in those situations, a full write log, table write log, basically. And so, don't think that consistency is still only a data store issue, so that you can get along just to leave that to the database. We have to shift that up on the application level. On the other hand, Counterfalls, basically, don't distribute your data or give up your serializable consistency model without explicit need, because distributed systems are hard, period. So they're hard to reason about, they're hard to understand, they're hard to operate. So if you don't need to don't need 3 replicas if one does the job. Don't shard your data if you don't need to shard your data. And don't go for base transactions just because you can. I mean, that's maybe fun in some other places, but here it's no fun, at least not for a long time. And as I said, I know very few developers who really understood the consequences of what's going on there. And so therefore, choose wisely and have your developers in mind whenever you do such a decision. That's the counterforce about that. Okay, let's wrap up. Was a whole lot of stuff in the last almost 50 minutes, sorry. So in the past, we have relational database and assets, which is a great programming model, but as we learned, asset does not usually necessarily mean serializable. Today, we deal with cloud, microservice, NoSQL, and base, which gives a lot more of options, but also a lot more challenges. And the pure base model gives us a very hard programming model, so be wary about that. In the future, people are trying, so at least in the research community, trying to exploit the boundaries and push the limits of highly consistency and highly available systems up. So they provide a lot of options between ACID and base, and so research so prototypical implementations show up. And on the other hand, the downside is we have to reason about that also on the application level and implement measures for that. So what I try to give you is some idea what options you have, basically, and how they work. And if this was all a lot too much for you, because it was quite a bunch in the last 50 minutes, and you just want to remember one thing, I wasn't sure which to pick, but then pick that one. There's no one-size-fits-all solution. As I said before, I put all the references on the slides. Here, it's quite a lot, yeah, and there's a lot to read, but it's very interesting stuff. And I will release them on my SlideShare account probably this evening or tomorrow. So if you want to review all that stuff, we'll have easy access to that. That's what I had to offer for you, and I'm absolutely surprised that I at least ended up within the 50 minutes. I mean, that was at least for 90 minutes of content. So thanks a lot for being that patient and yeah, having survived that. I hope most of you did without any mental illness. Thanks a lot. So as time's basically up, so I will hang around at the conference site till tomorrow in the afternoon. So come to me if you have any questions or suggestions or whatever, and please do not hesitate. Just do it. Thanks.